should we start? Or you have 2 minutes?
2 minutes
It
still.
was very awkward to stand here.
I know, sorry. It's like, should a train leave early?
Usually when it's this quiet this early, it's like, you're not going to get anyone.
Oh, there we go.
And that's what you do to start. Good timing.
A little conversation. I almost missed this because I was looking at the titles and I.
Oh, actually, it doesn't mention the Lucene.
Yes.
Yeah. Right. So I think that was a miss. Yeah.
Yeah. I was like, what's that about? I don't know. It sounds
Yeah.
very generic.
I think the description says it, but not the.
What kind of query cache are we talking about?
Exactly. That was yeah. Okay, I think we can start, I guess.
Yeah.
Well, yeah. So, hey everyone, I'm Sagar, and I'm here to talk about on Lucene query cache, its internals, the automation possible, and more. Also, just to give a background, Ankit was also supposed to join this, but I think he already gave 2 talks and it's pretty exhausted. I'm like, okay, I'll take it over. So also give a background, I've been working on the caching side of things in OpenSearch for the last 2 years. So I know a bit about Lucene query cache, and because we reuse the same implementation within the OpenSearch as well. So this is a little about me. As mentioned, I'm a software engineer working on Amazon OpenSearch service. I'm an active open source contributor to the OpenSearch project, primarily focused on the search and the resiliency side of features. I also have a couple of Lucene contributions, and hopefully I'll have more in the future. So I think before we actually move on, so this is one of the PRs. I want to talk about this first. So this is one of the PRs which Adrian opened, I think this year, disabling the query cache by default and making an opt-in feature starting in Lucene 11. So at first when I looked at it, I was kind of surprised because I think we use a lot in OpenSearch and kind of helps for a lot of customers. But I think I also realized, okay, this one of the reasons can be query cache is not very performant, is what I kind of understood, and which we'll also discuss later in the talk. Also, this I think this talk also makes it even more useful that we as a community can improve query cache as a whole, and maybe we can enable it back by default in the future, I guess. So. Yeah, so I'll just start with a high-level Lucene caching overview. So obviously Lucene uses caching in a lot of places. So I'm not going to talk about all those scenarios here. This is specific for the query cache, and so primarily query cache is essentially an on-heap cache designed for repeated queries. It actually only works for the non-scoring ones, the filter kind of queries, and it kind of caches them on demand. It also caches response at a segment level. Again, we'll see all those details in the later slides. So this is a high-level overview, how query cache works. It's a 10,000 feet overview, I would say. So here it kind of shows a Boolean query, which has a simple Boolean query which has a must and a filter query clause. So for every clause, Lucene checks whether the scoring is required or not. And for the must clause, obviously the scoring is required, so it will go the usual way of scoring and returning the results. For the filter clause, as there is no scoring required, it actually first checks whether the responses already exist in the query cache. If not, then it will actually calculate the results and then cache the response for each segment. So as you can see, this is again very simplified view. Query cache has all these segments. It kind of not maintains, it just tracks, and also tracks the corresponding query cache and the response for each segment. I mean, it has internally it has a map where the key is the segment and the value is a map of the query and the response. Again, we'll discuss this later more in the detail in the later slides. Yeah, so this is, I mean, a lot of people have actually talked about like how this index searcher, what is weight and all this stuff, but this is my try of capturing how the flow looks like when someone fires a Boolean query and how query cache actually comes into the picture. So as you can see, so when you fire a Boolean query or like any filter query, so it goes through the usual index searcher, creates a Boolean weight, and within that it goes over each clause and creates a weight for each clauses. During this weight creation, it actually checks whether the score is actually required or not. And if it is not required, the weight is actually wrapped inside something called a caching weight wrapper, which is actually provided by query cache, and this is how it actually uses it, to cache the queries and determine whether the query needs to be cached inside the query cache or not. So this caching weighting wrapper internally overrides like the scorer supplier method, and so when you start doing actual searches for each segment, cache eligible queries will produce this scorer supplier provided by the caching weight, kind of overrides it, and then where it checks whether the doc ID set is actually cached or not already for this query for that segment, and then if it is cached, then it will return the response back. If it is not, then it will return the response in form of a doc ID iterator, obviously. And then if it is not, then it will run the underlying scorer, collect the matching documents IDs, and then cache it before actually returning the response. Also, it does all these. I mean, everyone might be aware of this, like fixed bit set, and also it kind of determines. The query can actually determine whether it needs to cache doc ID set inside a fixed bit set or rolling bit set, depending like if it's like a very dense pack. Then it will maybe use a fixed bit set, otherwise it's very sparse, it will use a rolling bit set because it is like optimized for that particular scenario. So yeah, this is like it gives a more detailed view like how the query cache actually works. So query cache, so this talks about like the query cache structure. So as you can see, like this map. So this is like the high-level map which query cache kind of maintains. So it has like index reader cache key, and it also has this value as leaf cache. So this cache key is nothing but it uniquely identifies. As you can see from this snapshot, the code snippet is actually uniquely identifies a segment reader, and this is present inside the index reader class. So this is how it. So every time you create a segment reader or index reader, it will just basically this class gets initialized and uniquely identifies that particular segment reader. Yeah, so this is how query cache is able to like maintain like per segment query responses by using this cache key. And the leaf cache is nothing but like it's a map of the query and the doc ID set. So the query is obviously the key, and the doc ID set is the value. And because query cache is essentially an LRU cache, it uses this synchronized linked hash map with access order set to true, if you see right here, to maintain the queries in LRU order. So in later slide we'll see like, so this was kind of confusing for me at least to see like when I was trying to understand the code, like why is this like map query to query. But yeah, I think when I saw this access order true, then I understood, okay, this is how it kind of maintains the LRU order within the query cache. So it only tracks queries like and keeps queries in the LRU fashion, and corresponding caching the responses as well for those. So in addition to that, it also has this like all the read and write operations to both these map, like the LRU map and the main map. It actually happens, every read and write operation happen under the global read and write log. So apart from thread safety, this also ensures that we can have multiple obviously concurrent readers or a single writer at any given point. But yeah, I think we'll talk about this like the synchronized map and why it is actually kind of creating some problems and what is kind of we can do about it. Again, just giving how like the query cache invalidation works. So, I mean, in a nutshell, if any segment is getting invalidated, then you'll have to remove that stale like segment reader entries from the map or from the query cache. So this code snippet actually just it's taken from a put method call. So it actually is checking whether the leaf cache, which is basically the entries for that particular segment, if it is not there, then it will actually create that leaf cache, and then it try to put that key and the leaf cache. The key is basically a segment, and the leaf cache is nothing but the query in the doc ID set. And then right here, if you see, this is the one which kind of, so during the write call, I think it just register listeners for every segment, or like the closed listeners, so that whenever the segment actually gets closed, it can actually track that, and it can actually delete those stale segment entries from the query cache map. So again, this is the one method, the one below. I think again. So whenever a segment is actually getting closed during segment merges, then it'll actually call this, and then it'll try to remove the entries for that particular segment from this particular map or from this cache. So yeah, this is how kind of it works in a nutshell, the invalidation. So it has all these default caching policies. So it does provide an interface where you can actually inject your own custom caching policy. By default, it uses some usage tracking policy, something like that. It uses that policy, and by default, like the frequency is like, so it has a frequency-based policy where it'll track the frequency of every query, and it'll actually so by default the frequency is 5. So it has to see the same query 5 times before actually caches the response for that particular query. And there is like some frequency for the costlier queries, like point range and multi-terms is like it's kind of 2. So yeah, so it has all these hard-coded values and uses a ring buffer to track the frequency of the queries via this hash code. There's also this policy where it's called like the skip cache factor. So again, it's very confusing to look at. Like I have to wrap my head like what it does and how it kind of works. But actually, it tries to compare the cost of the clause, like compared to the top level query, and uses that to determine whether it needs to cache that particular clause or not. So this is, I think, needed because I think in a nutshell it just wants to avoid the clauses which are like large, comparatively large, because it can actually cause evictions and performance overhead. Because if you cache like a very big clause, you can just evict a lot of queries from the cache, and then it can cause a lot of eviction, and obviously it will cause a lot of performance overhead. Also, it only caches for a segment which has like 10K documents. Again, this is just to ensure that large segment entries are large segment entries are not often invalidated, and then you kind of you can maintain those queries in the map for the cache for a bit longer for those segments. Okay, so I think we have covered like how Lucene cache kind of works overall, and I'll start with like what are the current limitations like which exist as of today in the current cache design, and how I try to fix it, like doing some POCs and like some benchmarking. So this is like part 1. I've divided into all these parts, like it's about part 1 and part 2, like how kind of like identify all the problems, and then I try to like address them. So I think before I mentioned that this cache maintains queries in LRU order, which is like using this synchronized linked hash map. So I was kind of confused why it needs to wrap this inside a synchronized map, because I think we perform all the read and write operations under the read and write log. So it's kind of confusing, but I think the main reason obviously is like when you do a map, like a get on this map, so it actually does some internal reordering, because it needs to reordering to maintain the entries in the LRU order. So essentially it becomes a write operation underneath. So which actually, again, this is why we kind of need this synchronized hash map. Also, as mentioned that again, it's using a synchronized order, so it uses a global log to perform any good get or put operation. So even multiple get operations will actually get blocked on each other. So again, not very performant, but this is how it kind of exists.
Is that a per segment global lock?
Yeah. It's
Not
not
across
across
the whole
segment.
index.
Like this is like
Whole index,
yeah,
global lock?
like the whole cache level index. Yeah, cache level lock. This is not even segment lock.
Wow.
Yeah. So LRU cache has this global read and write logs, and so we protect this map under that read and write log. But again, this map also has like its own global log, which is used to protect its own like the internal ordering it does, because it has to maintain all these elements in LRU fashion. So it's like a log within a log. So it's like yeah. But yeah, so I mean, so it was very obvious that looking at the code, it has some issues. So this is actually one of the Java flight recorder snapshot I took recently during a time when a particular OpenSearch customer was actually facing tail latencies spikes and causing timeouts at their end. This customer actually had a very low latency and a high throughput kind of workload, and then they were very sensitive to any latency spike. So this profile was taken, like this JFR was taken for 5-minute duration and one of their open search data node. This actually shows, like, if you see here, right here, it shows the total log wait time, which is like 7 minutes, like 23 seconds. But obviously, it's distributed across distinct threads running parallelly, but still pretty high. Like if you compare like just a 5-minute duration profile, and also it shows you like what is the max block wait time, which is like around 38 milliseconds, which is pretty high because this is on a segment level, and it was causing pretty high latency spikes for this customer, especially like the P99 and P90s. So also you see the stack trace, it clearly shows the same synchronized hash map we were talking about in the previous slide. I think it is kind of blocked on that, which is obviously coming from the LRU query cache. So yeah, I mean so you imagine like OpenSearch has this multiple nodes, and every node has like multiple shards, and every shard has like multiple segments. So this kind of bubbles up the latency, and it was causing pretty high latency spikes for this particular customer. So this is the time actually I also, I kind of knew this problem, but I think it kind of became like, okay, can I try something and maybe do something about it? So I was curious, so I did some POCs here. So what I did was I replaced that synchronized hash map. So I just replaced and wrote my own kind of a custom implementation where I replaced it with a generic hash map. It doesn't have any loss in doesn't take any synchronized or a global lock. And then also for maintaining the entries in the LRU order, I actually wrote a simple implementation where I just used some doubly linked list, and I did some minor optimization on top of that. For example, I did some optimization on the doubly linked list, and also obviously because this LRU to maintain all these LRU entries, there are obviously a lot of mutating operation you need to do because there are many threads which can access this. And I again had to implement like a global lock kind of a thing which protects the LRU mutation. So it kind of looks the same way the way the synchronized hash map was working, but I did some like smaller minor optimization where I did some non-blocking promotion where I'll actually skip taking a lock if a thread is actually busy already doing some optimization. So it doesn't give you a very exact LRU guaranteedness, but I think it again it's a trade-off and it gives you like slightly more performance. So I did some benchmarking on this. I didn't see much improvement, which I was kind of expecting was 1.1 and 1.2x, I guess, when I ran some micro JMS benchmarks. The one thing I also did was to partition the cache. So right now it's like a single partition, you can imagine, and it has like all these global read and write logs. So what I did was I actually partitioned it, and so that we can reduce the global log overhead. But yeah, again, even in this, so this is the diagram which kind of, just trying to portray out like what exactly I did. So any query for a specific segment will always hit the same partition, even if you partition the query cache into multiple parts, because like the key itself in the cache it represents segment. So, and this is how I using to calculate the partition number in my code. So, which is why it will go. Any query for a specific segment will always hit the same partition. But again, this was like I wrote this POC partitioning and replacing and writing my own custom LRU kind of a logic, and I ran some benchmarks. So again, so I written some a custom JMH micro benchmark in Lucene JMH module. I think it has some tests written there, so I just use that module itself. I created some 50 custom cache keys. I created some 50 custom cache keys, which basically each represents a segment. I created a sample response which can be used across entry, which is basically a dummy block ID set, and also generated like end term queries which can be used for caching. And by default, I made all the queries eligible for caching. Again, I grouped to test this caching thing. I think I just grouped the workload or this particular benchmark into 3 workloads where I do like 100% reads. In the second, I do like a mixed load where I do 60% reads and 40% writes, and then the third one basically 100% writes. So I wanted to test all these scenarios of how it kind of behaves, like my custom implementation, and then see like whether it kind of gives me good results or not. So I did actually peek into Lucene util as well, but yeah, I saw that okay, a lot of existing benchmarks have actually query cache disabled. So I didn't take that route further, and I don't know if we have a very good workload for caching itself, like to test the caching itself. So that was something I think I didn't try that, which is why I kind of took the route for micro benchmarking and wrote something on my own. But maybe I can. We did something in open source. Maybe we can try and contribute back to the Lucene util as well, and I have something around this as well for the later part. So yeah, this is the benchmark results, which is basically for my custom implementation. So as I discussed, we do kind of represent our own custom implementation, and had created like 8 partitions within the same cache, and each partition has its own like logs, and so it reduces the overhead, increases the throughput. So if you see like the mixed load, which is like 60% read and 40% writes, it kind of gave you like 87% like gains. And the get only about like 45%, and write only was like around 24%. So it was pretty good, the results, the POC I wrote. But I think it's, again, there's one caveat which I'll talk about like in the next slide. So before we actually, I think let's actually go to this part. So as you saw,
I just have a question on the previous graph. I'm just wondering, right? I mean, it seems kind of weird that, like you are getting 45%.
Yeah, even I had that,
Because, like, it should be maybe some sort of average of the both.
Yeah, it should be much higher, you're saying, right?
Yeah, I mean, for the mixed workload, it is higher than both. That doesn't make
that was,
a lot of sense.
Yeah, that is interesting why it was happening. I ran it multiple times, but I took some profiles. I was seeing some some hash code, like query hash code, because I was doing a lot of stuff around that. But yeah, I'm not sure on that, like why exactly is that happening. But I think we'll have to deep dive into that.
Got it.
Because I have the same question, like why it is not the same, it should be more actually, but it is not so.
And another question. So here, the read writes are to the cache itself, right?
Yeah.
Not in terms of like segments get updated.
Oh no. So actually, I kind of missed it. So the way I did the micro benchmarking is I took the put and the get method call, which is kind of private in Lucene cache. I made it public, and I just kind of bombarded those 2 methods for this micro benchmark. So it's not doing anything. It's not doing any an invalidation or like anything in the background. It's just like pure put and put and get call. Sorry.
How many How many threads?
So this was 6. So it was 6 read threads and 4 write threads. And for get it was like obviously 10 read threads and 10 write threads for the write.
And there were more than that many cores in the box on the Mac.
Yeah, Mac had like 14 cores. So I think my Mac has, so we could have like further but I kept it at 6.
Did you saturate the total CPU? Were they all
no.
No. Wouldn't expect it to. They have to have some contention.
Yeah.
So it would be like fair to say that this graph represents the increase in efficiency, like it kind of measures the synchronization overhead. Between one partition versus 8 partitions. Right?
Exactly. Yeah. I mean that is kind of expected also, right? Because if you have all these global write logs, if you just partition it, like obviously you will get higher throughput because it's like uniformly distributing the request and it's not contending from the same log. Like it will just go to some other partition and just run faster, I guess, right?
There is no hot partition in this case.
In this case, there is no hot partition, but I think I will come to that in the next slide. Why this? Oh, sorry. Yeah.
So when you mentioned the lock in the baseline, what kind of lock is it? Does it allow like read lock for read access?
You're talking about lock, right?
Yes.
Sorry, lock?
Yes.
Yeah. So what kind of locks?
And is it using the pattern where you do the read lock for read operations and write lock for write operations?
Yeah.
Or is it global single same lock for everything?
I mean, there are 2. So there, especially with the one I showed, like the synchronized link hash map before. So we have read and write lock for the query cache, which kind of protects any use for the thread safety and protects any. So there's only one writer writing to the cache at a time, and there can be multiple readers. But even with that, we have this synchronized link hash map, which I was talking about. That also has its own global lock. It's a synchronized hash map, so it's like a global mutex lock. So even when there are like multiple readers within the cache, it will still contend for the same global lock for that particular map when it does a get. So even with multiple readers, they're still contending on a common lock, which is which on this map, which is kind of maintains the queries in a LRU fashion and uses all these synchronized or like a global log. So it's kind of confusing, but yeah, it's kind of written in that way. So even in my approach, what I did was I separated this like the internal ordering you need to do for the LRU. So you need to maintain a LRU list. So I did my own implementation where I'm using like a doubly linked list, but I still need to like maintain or protect that doubly linked list for any mutating operation. So I don't do that inside the read log, which was happening right at this point, but I kind of do under a different kind of a global LRU log. I don't know if it was that clear or not, but I think we can maybe discuss later. Yeah, but we can discuss more on this. So I'll come to the part 2. So I think we saw like, okay, there was great improvements, but there is a cache to it. So I did divide this cache into 8 partitions to improve the throughput, but what I could have increased to like 16 or 32, and I could have maybe have more performance and more throughput, but actually doesn't help with the current key structure. So if you see this map, again I'm adding this snapshot. So the key itself is the segment itself, so it represents segments. So for example, if you have one big segment and you have like n concurrent queries trying to read or write into the segment, it will actually, so because it has, in this case, for example, if you have 8 partitions and there is a one, in your use case, you only have like a one large segment, so that particular segment only will get mapped to a particular partition. And which is kind of, again, it will not solve the problem because, again, all the n concurrent queries will again go to the same partition, which that segment kind of represents, and again, it will contain for the same kind of global logs. So actually it doesn't help in this case when you have like one large segment or like few segments, and even if you partition it, it will not help because again, so one partition will actually become a hotspot because you only have like one segment. So this case, so the previous approach actually works well, but only works well when you have like too many segments, and it doesn't work well for this particular scenario where you have this I guess one large segment. So again, this was a problem. I think I tried to see what can be done. So again, I kind of did some POC. So if you see this, like this code snippet, so what I did was instead of having the segment as a key in the cache, I created like a composite key. So composite key actually has this cache key, which obviously represents a segment, and also it has a query itself. So now when you kind of, so now what happens is even with one large segment and n concurrent queries, you will actually, using a hash function, you can use a segment and the query and uniquely like generate a hash code, and you can, via that hash code, you can uniquely assign that particular request to a specific partition. So that actually overcomes the problem where if you had in the previous approach, you have a single segment which will always get mapped to the same partition. So I created this composite key. Again, I still borrowed the idea of like partitioning it. I created this composite key, still had the partition kind of approach where it kind of, and this actually distributes the request pretty uniformly across partitions. So, and obviously, as mentioned, it works well with a single segment. Invalidation actually becomes a little trickier because what happens if, because now I'm using a composite key and a particular segment actually gets invalidated. So now when that happens, you have to actually, because you don't know which entry, which entry has this stale segment which got actually closed or during merger. So like in a naive way, you can actually just go with every invalidation, you can, or with every segment getting closed, a particular segment getting closed, you can actually iterate over all the cache entries and see like which entry has this stale kind of segment and then kind of remove it. Obviously, it would be very expensive to do that, but I think one way you can do it, which I also kind of did it, is you can keep collecting those stale segments in a set, and then on a different thread which kind of runs like maybe every 1 minute or every 30 seconds, it's kind of iterate over all the cache entries and try to clear the entry which kind of has a stale segment. So yeah, you can use a different thread and you can maybe bypass this problem and not do it every time during the segment getting closed. So yeah, this kind of works well compared to the approach I was talking about. So yeah, again, the benchmark for this approach and it was pretty good actually. So the V2 again represents my custom implementation. I again created like 16 partition for the query cache, having its own read and write log, and then obviously I was using a composite key. So in this case, so this concurrent get input is again like a mixed workload, and 60% reads and 40% writes with 6 reads and 6 threads doing reads and 4 threads doing writes. So it was like, compared to baseline, it was like almost 4x of the improvement that I saw when I did the micro benchmarking. So this get performance and put performance, it just represents the what do you say? It just represents the get and put performance as part of the mixed workload which I was running. So it looks confusing, but yeah, that's what it is. So the concurrent put is actually 100% write workload. Again, I saw like 4x kind of improvement. I don't have the numbers. I don't know why I don't have the numbers for the 100% reads. Maybe I missed that. But yeah, that also kind of had like a huge jump in this in this performance. So yeah, so pretty good. Like I also note here, like I didn't benchmark with the cache invalidation logic, which and doing those cache cleanup in an async manner. So I think that if you include that, the performance would be slightly lower than this. But I think it should not be much in cases where we don't have like frequent or frequent merges happening, segment merges happening in the background. So, but yeah, it should be lower than this, but I didn't do it as part of this micro benchmark. So before I actually move on, I also want to mention that I haven't raised the PR for all these optimizations yet. I did raise an issue some time back, but I think it's got derailed and I didn't focus on this. But I think maybe should prioritize this soon, and maybe I also wanted to run a real simulate a real workload with some cache hit ratio, good cache hit ratio, and try to see like how it kind of behaves in a real real world scenario. Maybe I try to look at Lucene utils, but I think I didn't find much. So, but yeah, maybe I'll try that and try to have this create a PR on this.
I think this 8.16x doesn't look correct. I don't know, because it seems like the scale is very similar to the concurrent puts. So I don't know, maybe like.
So this is, by the way, this get performance is not the 100% read workload. So this is the read. This is a read performance or the read throughput in a mixed workload. So when you do a mixed workload, like 60% read and 40% write, also gives you like individual get and write performance when you do that. So it's actually part of that. Did I make sense on?
I mean, I think that is fine, but I'm assuming like whatever it is, right? It is same for V1 and V2. So compared to V1, I think the scale looks very similar to the like rightmost one.
Like the get performance says 8.16x, but it shouldn't be twice as tall as the 4.44x. It looks like it's not drawn to scale.
I mean, yeah, probably.
Yeah.
There's some one bar below 0%. I'm trying to make sense of the y-axis.
Yeah, this is actually,
Because I think other ones make complete sense, right?
Yeah.
They look relatively.
That is true. Yeah, actually, I didn't notice that.
I mean, yeah,
It looks like 3x.
Yeah, actually, it looks like 3x. So by the way, as a disclaimer, I use the AI tool to generate this. I should have done that. I should have done that. And then here a clear miss.
Mystery solved.
I'm surprised that any of them.
I think I should add the numbers exactly and then not rely on all these AI tools to generate all these.
I'm very gullible. Are you serious?
Yeah, I'm serious.
Tell us which AI it is.
It's ChatGPT, by the way, so I'll start down.
And this may get the 0%
Put the numbers in and it is. I do it.
But yeah, I think that's what I should. Okay, I think let's move on. That was awkward. So yeah, I mean this is a few of the further optimization I think which is possible, and then I was thinking about it. I think I just put it in a single slide. So I think there is also a way we can avoid even doing a log-free implementation where we don't require any logs to perform any mutating operation, but it's actually non-trivial, and I did give it a try, but it's not, I didn't get far. So I mean, caffeine is one library, like it's pretty fast, and it actually does all these log-free things, and even the eviction policy actually uses it pretty fast. So So that is one library. Maybe we can try it in Lucene. I don't know if how Lucene folks would be okay like taking that inside a module or something like that. But I think it would be pretty useful if we can try that out. It's the fastest library I know, like Java library which exists as of today. So, and what I was trying to do like with this log tree and everything, Caffeine actually already does it. So I don't think we need to write our own kind of custom logic, right? So yeah, that is one thing we can maybe try it out. So another idea I think we had, like for example, for use cases there are too many cache evictions and there is like an on heap is not sufficient to kind of hold the data set. We can also try using disk as a cache. I mean, it looks not, like counterintuitive, but I think disks are getting faster and it actually makes sense if you can store the responses for the expensive queries and just get the doc ID set for that particular query. And also like memory is also obviously finite and costly, so obviously not possible to increase the on-heap cache always in a lot of scenarios. So yeah, this is actually talking about the way like a tiered model. Instead of like just using disk as a cache, I think we can like have a mixed approach where we use like a tiered model where we have the on-heap cache and the disk cache. So obviously where we use the best of the both worlds. Like on-heap cache is fast and limited, but disk is relatively slower, but offers large. Yeah.
How would you serialize the queries in general?
Yeah, that's a problem. Like I did look at the query cache implementation, and it's even like serializing the query and the response. I think a lot of work has to be done.
Even I don't think in general like the query interface even has like
it doesn't have anything, so it's not serializable.
It might toString but it might not.
Yeah, it's not possible at this point. Yeah, I did give it a try, and it's like I did some hacking also, but interface doesn't provide any way to kind of do this. So again, that's kind of a limitation at this point. I think we also did this thing for the OpenSearch, like where this is the one. So OpenSearch, where we actually have this request cache. So request cache actually works pretty not like similar to query cache, but it essentially like caches the query the response at a shard level instead of doing it per segment level. So where we actually use this. And we had, but again, we don't like have the query itself, and we didn't have the challenge to like serialize the query itself. But actually, we did implement tiered caching in OpenSearch for the request cache, and we did all this like this cache can be dynamically enabled if needed. And we also had these policies where if you're trying to, it's like a simple spillover strategy where we did in OpenSearch where any query getting evicted from on-heap cache. We check whether the latency of the query is high enough to put into disk cache, because if you put like very cheap query into the cache, it doesn't make any sense because you'll be doing more often read and write, and it'll just hamper the performance altogether. So we did all these optimizations, and also this kind of represents like one of the stats for the query cache, the request stats in OpenSearch, where it actually kind of works well, where if you see there's a lot of evictions happening. So this is a domain which only had the on-heap cache, and it has a lot of evictions, and the hit count, like the hit ratio was pretty good, like I said, 70%. And then, so this is one of the use cases where actually having this tiered cache kind of model actually kind of makes sense, and it'll give you some boost, which also we saw when we ran some benchmarks in OpenSearch as part of this. This is again a very wild idea. I don't know I should be talking about it, just mostly talk about predictive caching, where we can actually so at this point, like we depend on these frequency-based kind of policies, and then cache the queries on demand. I mean, what if we know like these are the queries which kind of often are getting hit. We can even during like indexing time or whatever, like segment getting merges and getting routed, to actually pre-warm the cache and then automatically cache those queries into the cache itself. So again, it's a very wide idea. I'm not sure how we I haven't looked at the code or how we can do this, but again, it's a pretty wide idea at this point. So these are some references, like the tiered caching I was talking about, and like this Apache Lucene, this issue actually had opened some time back, and it talks about the same partitioning and the custom LRE logic I kind of wrote back then, and it also has this micro benchmark and how I kind of did it back then. So it's kind of a useful link if you want to kind of see that. That's it. Thank you.
So you mentioned in the beginning that there's it has to reoccur 5 times before it's cached. With your improvements, do you think that 5 times
is required or
a
not?
good idea or not?
I mean, it really depends. I mean, you can reduce it. So there is a way. So it does like Query Cache does provide you a way to like override that caching policy. And you can write your own. But it might make sense that yeah, maybe we reduce it further. But again, it depends. Right? It depends on your workloads. If you are getting repeatable queries again and again, you might reduce it like and not like wait for like 5 times because you will have all those misses having for the first whatever five misses, yeah, during those reads. But yeah, it might be possible for sure.
Do you know how old that original Lucene issue was that mentioned? The one that you had on that
The
slide?
Adrian one?
Yeah, the 14 what something.
The first slide, right? That was talking about.
The last one. Yeah, just
Oh.
passed through it.
This one?
Yeah, there's a Lucene issue there.
Yeah, this is opened by me, so.
Oh, you
yeah,
opened it. Okay.
I opened somewhere in I think March.
Okay.
Back then I was Adrian also like mentioned I'm disabling query cache, and I was kind of okay, why are we doing that? It just got me curious, and I just got and implemented some POCs and had some benchmarks done, and then I posted that issue on that. Did an issue on the Lucene itself, so that is mine. Yeah.
You mentioned caffeine. I think one of the reasons earlier Lucene didn't like caffeine was because it used unsafe.
Yeah.
And I think that changed.
Oh, is it?
Ben Main's like.
Because I remember the author of the caffeine, Ben.
Ben
He
Mains.
also Ben Mains. He was pushing. He had some ideas around like using caffeine within query cache, but I think he got some pushback. And I think he didn't go further from
Okay.
that point. Yeah. I remember that. I opened a lot of query cache issues in the past.
Quick
Yeah.
question. Okay, is the query cache? I forget. Is it pluggable so that if Solar or whatever wants?
It is pluggable, yeah.
Okay.
Yeah.
And do you think? Does it look like caffeine cache would be easy to plug in? Ideally, it would, because it's a very simple interface. I want to share, by the way, that Solar transitioned at some point. I'm really glad I recommended it at some point, because I saw we had several cache implementations. Each one had its own maintenance headaches and expertise around it. Like, what are we doing here?
Yeah.
This is a solved problem. There's this awesome cache that lots of projects use. Why don't we just use caffeine cache? And I'm so glad we made that decision in Solar. Not this specific mechanism that you're talking about.
Yeah. But it should be. I think it should be pretty much possible to do that and plug it in.
Yeah, it's not LRU, right? But
Yeah, it's not. I mean, it uses some
it might
tiny
affect a similar.
It uses a much better eviction policy
Yeah.
compared to like a simple LRU. So, yeah.
I mean, I guess yours is frequency and LRU, so it is kind of frequency based, like.
Yeah, correct.
In a way.
It's kind of it's kind of
Yeah.
hybrid. I would say. Yeah. That is true. Yeah.
Yeah, I'm very naive in terms of like my cache related knowledge, but I was just wondering, like, I think the bottleneck here is on the query serialization and the space used by it, and then the results as well. On the key side, I think
I mean, not the serialization part. So I don't think that's
not the serialization time, but ultimately you will be loading it on heap, and then it will be taking more memory. And then that kind of limits how much entry you
So
can
when you
have.
say loading onto heap, like what do you exactly mean? Like
Basically, these are on heap, right?
yeah.
So, like the more entries you have, the
Yeah.
better your cache will be, right?
Yeah,
So,
yeah.
like if you can just, like my question was more around like if we can use some sort of encoding scheme if we are not
Also-
using already. So, because most of the time what happens, like if you look at a query, you will have the same syntax. Your range might be a different one, or the term might change. But
Yeah.
most of the other content will be similar. Right?
So you're saying we can reduce the space if we do that.
Oh, with the query.
Yeah, for the query.
For the query, not the value, the docs, but the query.
Yeah, I was coming to the value as well. So for the query itself, like the key size would reduce, right? This way.
But again, you have extra like whatever
Overhead of-
encoding decoding, right? So I don't know
Sure.
if it makes actually sense if you're just doing on heap. So
Sure.
and a query cache has all these mechanisms. It will not cache like a very big response in case it just hampers the performance. So it has all these kind of operations within that. So it actually calculates like a query size, even and kind of rejects the request if it's like just too big.
Yeah, and on the response, I was also wondering like if a columnar format might make more sense because you can just compress a bunch of things that way.
I'm not sure on that, like how would that work. But yeah, maybe we can. I don't know. We can discuss. But how do you see it? Like I don't know. Call it that.
Yeah, I mean definitely there would be more overhead in retrieving, but I feel like you can have more in your cache. And it's
Maybe.
always a trade-off between
Yeah.
it's a zero something, right? So,
Yeah, I don't have an answer for that. Yeah, that's the point.
If I'm not mistaken, this is using very, very optimized and well-used doc ID set
right.
caches
It's
already.
not storing any
Very
fields.
efficient.
Oh,
It's
okay.
not storing fields.
Right, there's
Doc
no
ID,
fields.
like
No.
Doc Ordinal.
Oh,
It's
so
not-
yeah,
it's
the
not
response
cache
is just the
doc-
bit set.
Cache doc-
Yeah.
Oh, okay.
Oh, sorry, I didn't. I was just talking. I thought you were talking about query and all that stuff, but
Yeah.
the response itself is just the bit set. Like,
Got it.
you just use the bit
Yeah,
set.
sure.
Yeah, it doesn't. Sorry, I missed that.
I just have one suggestion. Since throughout your journey, you're already abstracting out, like we're dealing just with two APIs, get and put, right?
Yeah.
That already suggests, if you want, you can read the rest of the code pretty generically and leave the holes only for get and put. That allows us you to plug in different cache implementations
Yeah.
very quickly.
Exactly.
Even that can become a user choice. So,
Yeah,
yeah.
that is true.
So
Yeah.
user could use
Yeah.
caffeine or whatever.
So yeah, that is actually that's a good point because right now it gives you an interface, but it doesn't give you an interface to override get and put. It's like a private method, so I think I'll have to change the structure itself if you want to make it more pluggable. That's a good point.
Yeah, it's almost like asking the user to initialize an index search
Oh, yeah.
with a cache implementation.
Yeah, that's something you can try to do that. If you want to make it more pluggable, I think, and if you want to try caffeine, I guess.
Yeah, and then you are not forcing Lucene to pick a cache dependency. That way.
Yeah, that is true. Yeah, that is true.
Yes.
Yes.
Like the only place where Lucene itself does the sort of caching, rather other places where you might benefit from a better implementation.
Oh, yeah, I'm not sure on that. I mean, uses a lot of places, but yeah. So you're saying whether you can extend some other use cases or?
I was curious, like, if you want to change this particular piece of code, are there other pieces of code in Lucene itself where people also do caching, which you probably want a generic solution?
Yeah. So you're saying, like a generic kind of a cache for the whole Lucene?
Yeah, not just to do the one point optimization, but look across the code base and see what other places might need a similar rewrite,
Yeah.
if at all. Or maybe ask the question, why does Lucene itself need to cache queries? Like Solar does its own implementation on top of Lucene, perhaps OpenSearch.
We don't. We use the same. Yeah, it doesn't give you many hooks, so yeah.
I don't
Yeah.
know of other
Lightspeed.
places
Okay.
where Lucene caches. I don't know of any other places where Lucene caches.
Why does Lucene need
What?
to cache?
I know. I don't know why it does. I mean, it's off by default. Maybe it should be removed.
Well, it has been on, and that annoyed me because everywhere in Solar we had to flip it off.
Yep.
And I didn't like anyway.
Yeah.
I speed.
Yeah.
I didn't ever. Okay.
Yeah.
So just to add on to something, I think the reason why Solar disables this thing, and I think the primary reason is because we want to give users control. So we let so Solar has its just FYI. So Solar has its own cache on true false per query per particular filter. So that way you can make a specific choice. But it's a little different. I mean, these are not exactly the same. On one hand, what I do like about this is that there's some heuristics inside of this cache, which I think is pretty clever. It can look at how many, it's segment level, and furthermore, it's like looking at how many docs in a segment and what kind of query it is. So there's some nice heuristics there. I've always wondered at the Solar layer, we just basically say we're always caching it unless the user says turn it off. I've always kind of wondered like how well some of those heuristics work, because I've heard that, for example, I've heard the term query is just so simple and good on its own that it doesn't really need.
So it actually Lucene avoids caching like very cheap queries, for example, term query. So it'll actually not use it. So by default, it has all these caching policies and it just avoids like caching those kind of queries. So yeah, it does that as of today. What was the other question, or was this the only one? I guess you had another question.
No.
No. Okay. Okay. If no one has any questions.
Yeah.
Thank you.